Now in this slide we will study about the pressure, the definition of the pressure. Pressure is perpendicular force per unit area. So we can define the pressure force per unit area. So if I write the formula for the pressure, so this is the force per unit area. This way we can write the formula. And now if we make the unit of the pressure is, now the unit of the force is Newton and the unit of the area is meter square. So this is the standard unit of the pressure, Newton per meter square, and this Newton over meter square is also known as Pascal. This is also known as Pascal, and in the short form we write the Pascal PA. So here this is 1 Newton meter square. This is 1 Newton meter square is equal to 1 Pascal. This is the standard unit of the pressure, but other units are also we are using, and these units are non-SI units. We can define the pressure in those units, but we cannot use for any scientific calculation. For the calculation point of view, this we cannot use. Now the one is, this is the number one, the non-SI unit. This is atmosphere, and in the short form we write ATM. So this is ATM, and 1 atmosphere is equal to 101.3 kilopascal. So this is the one relation between the 1 atmosphere and the kilopascal. So 1 atmosphere is equal to 101.3 kilopascal, and here this one atmosphere is also equal to 1.013 into 10 to the power 5 Pascal. So what we did here, this kilo, this one, okay, here this kilo means this is 10 to the power 3 here. So what we did here, how this and this is same. So this is 101.3 and it is multiplied by 10 to the power 3, and this is Pascal. And what we did, this decimal it is coming here, so this decimal it is coming here, and now this is two digits we are getting from here. So this is 1.013 into 10 to the power 5 Pascal. So this way we can write the Pascal, and this is equal to 1 atmosphere. So this is the relation between the 1 atmosphere and the Pascal. Kilopascal you cannot use. If you are using this relation, if you are using this relation, this one, so directly this number you cannot use 101.3, because here this is coming kilo, so you have to change kilo and then you have to use, because the unit of the pressure, is Pascal, not kilopascal. We cannot use kilopascal. So this kilo you have to change. Okay, so the meaning is, if you want to use Pascal, so use this number. Okay, for example, if I say, okay, so for example, if I say the value of the pressure is 5 atmosphere, so this 5 atmosphere we cannot use, because this atmosphere is not the standard unit. Now what you have to do, you have to change this atmosphere to the Pascal, and now the relation between the atmosphere and the Pascal is this. So what you have to do, now this is 5 multiply by 1.013 into 10 to the power 5, and this is Pascal. So after multiplying this, so this pressure will be in the Pascal. What after the multiplication, what it will come here? So you have to use this number for the calculation, like that. And there is a one more unit, and this unit is, and this unit is a bar. This unit is a bar, and this is also non-standard unit, not a standard unit. So 1 bar, this is 1 bar is equal to, 1 bar is equal to 10 to the power 5 Pascal. So this is one more relation between the bar and the Pascal. So 1 bar is equal to 10 to the power 5 Pascal. Like for example, if the pressure value is given like this is 3 bar, so this 3 number we cannot use for the calculation because this bar is non-SI unit. This unit is not the standard unit. You have to change this to Pascal. Now this unit you have to change to Pascal, then you can use. Now you have the relation that 1 bar is equal to 10 to the power 5 Pascal. So this 3 will be multiplied by 10 to the power 5, and this is equal to Pascal. So this relation is equal to this 3 bar, and they are same. This is equal. So this number you have to use for any calculations. So some detailed information you can find in this link. The link is given here. So when we are clicking on this, so this information we can find here about the pressure.
Hello, and welcome to another Science Man digital lesson. Today, we're going to look at the topic of pressure. Specifically, how is it measured? The important thing to consider is how pressure is calculated. Pressure is equal to the force exerted divided by the area that the force is acting on. Consider, for example, an area of 1 square meter. If a force of 1 Newton was applied to that area, then the pressure would be equal to 1 Newton per square meter, or 1 Pascal, the unit of pressure named after a famous French scientist. So a Pascal is a pretty easy to understand unit, but unfortunately there are many other units of pressure in use that can sometimes be confusing. The thing to keep in mind though is that they all describe the same thing, the force exerted on a particular area. For example, one of the most common units of pressure is the kilopascal, equal to 1000 pascals. It's used because the Pascal is actually a very small unit of pressure, so the kilopascal is a bit more practical. Some units, such as pounds per square inch, are used out of tradition. You'll see PSI used often to describe different pressure abilities and settings on hardware devices, such as the air compressor. Air compressors are simple. They use a series of compression cylinders to squeeze air into a smaller space, thereby increasing pressure. You can read and set the pressure of an air compressor using the attached barometric gauges. The word barometric literally means weight measure, coming from the Greek word baros for weight. This leads us to another unit for pressure, the bar, which was introduced by meteorologist Napier Shaw to describe atmospheric pressure. 1 bar is roughly equal to air pressure at sea level. Meteorologists commonly use the millibar as a descriptor of pressure on their weather maps. You've probably seen this on weather forecasts, where the areas of high pressure and low pressure are marked in efforts to predict the movement of weather systems. Air will always move from areas of high to low pressure. This causes wind, and combined with the rotation of the Earth, contributes to the circular nature of many weather patterns. Speaking of weather patterns, one of the most devastating hurricanes was Katrina. A hurricane has a low pressure eye at the center. Meteorologists often use a hurricane's eye pressure, along with wind speed, to gauge its strength and potential for destruction. Katrina's lowest eye pressure was 902 millibars, or 26.6 inches of mercury. In some parts of the world, inches of mercury is the preferred unit for describing atmospheric pressure. This unit is a holdover from early barometers invented in the 1600s, which were essentially a column of mercury in a tube with a pool of mercury at the bottom. As atmospheric pressure increases, air pushes the mercury higher up in the tube. You don't need mercury to make a good barometer. You can make one yourself with a simple jar, balloon, a straw, and some tape. Take a round balloon and cut off the end, then stretch the piece of balloon over the mouth of the jar. In order to ensure a good seal and to keep the balloon in place, use tape to secure the balloon by running tape all the way around the top of the jar. Now, all you need to do is take a straw that has had the tip cut into a point and tape it to the balloon at the top of the jar. By doing so, when atmospheric air pressure increases or decreases, the air in the jar will be squeezed or will expand, resulting in a collapse or bulging of the balloon. That causes the tip of the straw to move. You can track
In this slide, we will study about the atmospheric pressure change with altitude. So here we are talking about the atmospheric pressure. We are talking about the atmospheric pressure. So the meaning of the atmospheric pressure means this is the pressure of the atmosphere. So this is the pressure of the atmosphere. Atmosphere means of the air, of the environment. So this is the pressure of the atmosphere. We are not talking about the pressure of the gas in the cylinder. So this is the pressure of the pressure of the atmosphere. Change with altitude. Altitude means the height. So this is the height. Okay, this is the height from where? The height from the sea level. So if I say this is our earth, so on the earth there is a sea. So you say here this is seawater. This is a seawater, and this is sea water here, and also some mountains are there, like these are some mountains like that. So these are the mountains. These are the mountains. So what we are doing, like if I say this is 0 meter or 0 kilometer. So when we are going up like this, when we are going up, okay, in the air, so this height is known as the altitude. This height is known as the altitude. This may be in meter, this may be in kilometer. So here we are going to learn, when here at the sea level the pressure of the atmosphere, it is fixed, and this is 1 atmosphere, and the value of the pressure is 1 atmosphere. In terms of the bar, this is in terms of the Pascal, this is 1.013 into 10 to the power 5 Pascal, we can say like this. So at the sea level the pressure of the gas, this is 1 atmosphere, and this value is fixed. This will never change. This value is fixed. Okay, this value. Now when we go up, so when we go up, so what happens? The pressure, what happens? The pressure decreases. The pressure decreases when we are going up, so the pressure is decreasing. But here, this we can say this is the maximum value of the pressure. So the maximum value of the pressure is 1 atmosphere. If we are going up, so this pressure will be less than 1 atmosphere. So now here I have one graph, and on the x-axis of the graph we are taking this atmospheric pressure, and the unit of the pressure here, it is in kilopascal. So it is in the kilopascal, and this is the altitude. So this altitude means we are going above from the sea level. So here the sea level is this line, this horizontal line. Here, this horizontal line, this one. So this line is a sea. This is a sea level. This is a sea level. So we are standing on the sea. So here, this is sea, means it is 0 meter or 0 kilometer. So if we are going up, so this is 0 meter. So at the 0 meter, the value of the pressure is coming. The value of the pressure is coming here. So this is the value of the pressure coming. So what is the pressure coming? The pressure is coming 101.3 kilopascal. So this is the value of the pressure, atmospheric pressure at the sea level here, at here. So this is the value of the pressure when, this is the value of the pressure when altitude, when altitude is 0 kilometer, no height, like this. So the value of the pressure at the sea level is, this is 101, exactly 101.3 kilopascal. Now what happens if we are, see, this is like, this is 5 kilometer, so this is 1 kilometer, this is 2 kilometer, and this is 3 kilometer, and this is 4 kilometer, this is 5 kilometer. Now as we are going up, so up means if we are going 1 kilometer above, see here, so the pressure value is coming approximately 85. So here this is coming 85, and this is kilopascal. So the value of the pressure is decreasing when this is 1 kilometer, here 1 kilometer. So if you are going to 4 kilometer, so the 4 kilometer, so this is pressure, this is the pressure line, and this is the pressure graph. So it is coming here, so it is coming 60 kilopascal. So if you are going up, say this is 8 kilopascal, 8 kilometer. So at the 8 kilometer, if you see, the pressure is coming near about here 32 kilopascal. Now whenever you are going up, so this is 15 kilometer. So at 15 kilometer, the pressure value is coming, the pressure value is coming here 15 kilopascal. So this is coming 15 kilopascal when the altitude is 15 kilometer, like this. So the graph between the altitude and the pressure is like this. So it is decreasing. So this is the graph between the altitude and the pressure, atmospheric pressure. So this graph is always like this, the decreasing graph. So here this is the pressure and this is the altitude, so the graph will be decreasing. Barometer, the definition of the barometer is it is a device to measure the atmospheric pressure, and this formula we have to use to calculate the atmospheric pressure. And on the right hand side, this is the device which is used to measure the atmospheric pressure. Now here the difference between the gas pressure or the air pressure. The air pressure, when we say the air pressure, so this is when we say the air pressure or when we say the atmospheric pressure, they are not same. So if you see here in this picture, so here the air is inside the tire. So this machine is used to measure the air pressure inside the tire. This is the air pressure, and atmospheric pressure is also the air pressure, but this air pressure is inside the tire, and this atmospheric pressure is the pressure of the air on the earth's surface. So this atmospheric pressure means this, suppose if I say this is the earth, so on the earth there is a air like this, okay, so this is the air, so there is a air pressure on everything. So this air pressure is known as the atmospheric pressure, not the pressure. Atmospheric pressure is not the pressure in the tire or in the cylinder. So the atmospheric pressure means the air pressure on the earth's surface, or anything which is present on the earth, like we are standing on the earth, like this. So any human standing on the earth, so on this human being the air is putting some pressure like this, so this is the air pressure, on the human. So this air pressure is known as the atmospheric pressure. So now we will talk about the device. On the right hand side, the machine is given, the device is given, and this device is known as the barometer device, which is used to measure the atmospheric pressure, the pressure of the air on the earth's surface, not the pressure of the tire, not the pressure of the cylinder, only the pressure of the air which is present on the earth. So according to the construction of the device, here in the red color, this is a reservoir which is used to fill some fluid or some kind of gas or some kind of material or the medium. In this case, mostly in 99% cases in the barometer, this mercury is used. Mercury is a metal in the liquid form. So in the reservoir, this reservoir is filled with the mercury. This brown color, this gray color is a mercury. This is the mercury. So it is filled with the mercury, and there is one glass tube, and this glass tube is attached to this reservoir. It is attached here. You cannot see full diagram here, but this glass tube is attached with this reservoir, and this glass tube is same as like a thermometer. You know about the thermometer, is same like thermometer. And here this is the scaling, okay, this is the scale present on this, and this scale maybe sometimes in the it is in the millimeter, or sometimes it is in centimeter, or sometimes it is given in both the units. Now here this scale may be in centimeter, or this scale may be in millimeter. Let us suppose, and this scale starts from here. This is first marking. So first marking means this is, if I say I will take in centimeter, so this is 0 centimeter here. This is 0 centimeter, and if you say this is 10 centimeter, and this is 20 centimeter, and this is 30 centimeter. So likewise this scale is going up like this way, like this way, like this way. Okay, so suppose if I say this is some scale, it is 40 centimeter and it is 50, like this. So the scale is going up. Now how this barometer is used to find the atmospheric pressure? There is no direct reading from this barometer device. So what we have to do, one parameter we have to find, and this parameter is a height of the mercury. Height of the mercury is, when this it is 0, so this mercury will go up, 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 and like this, and it will keep on rising, and at one time will come when there is no rise in the mercury, it is stop here. Suppose we say, if this is if I say this is 100 centimeter, so this is reaching at 100 centimeter. So beyond this level the mercury is not going up, so it is stop here. So we say the distance between this line, the last where the mercury is going, and the distance from the 0 line. So this is the 0 line here. So this we say this is the height of the mercury. So we say this is the height of, sometimes we say the height of the mercury, or height of the barometer, or the height of the tube, or height of the column. Many names are there, and this height is denoted by H. And this, most of the scales are they are in centimeter, or they are in not in meter, and they are in millimeter. So we can take the reading, or in some barometer centimeter is also given and the millimeter is also given. So this is up to you which scale you want to use, you can take the reading. So from this barometer the reading of the height will come maybe in centimeter or maybe in millimeter. Now there is one formula, the formula for the formula how to find the atmospheric pressure. So this formula is given, the atmospheric pressure is equal to P equal to H, D and G. So in this formula, what is H, D and G? This H is the height of the fluid column. So this H is a height of the fluid. Fluid means anything. Fluid means which is filled here, So like in this case it is mercury. Sometimes it may be some water or some any other liquid, but most of the time in 99% cases in the barometer this mercury is used, sometimes some other. And this height in this formula you have to take in the unit of the meter, but from the barometer this height will come in centimeter, or this height will come in millimeter. So what you have to do, like if you are getting this height, suppose it is coming 100 centimeter, your reading is coming 100 centimeter from the barometer. So this height you cannot use in the formula, because in the formula you have to use only in meter. So what you have to do, you have to change this to meter. So 100 centimeter is, this is 1 meter, like this. So this 1 meter, 1 you have to use in the formula, okay, in the formula here for the H. Now this H, D here you have to use for the H, and for the D is the density of the liquid, density of the fluid. And this density of the fluid is what we are using here. Suppose I am using this mercury, so this density I have to take the density of the mercury, and this density of mercury is constant. Density of the mercury never changes, this is the constant value. Or anything else, if I am using here water, so here if I am using this water in case of mercury, so the D in the formula, so this D means the density of the This D means the density of the fluid in the unit of kilogram per meter cube, and this value is constant. Maybe if we are using mercury, even then it is constant. If we are using water or any other thing, so the density is a constant property of the materials. Suppose if we are using mercury, so for the mercury, like for this is Hg means mercury, so this Hg means this is mercury, so this is mercury means, so for the mercury the value of the D is 13,600 kilogram per meter cube. So it means this number for the density, it is constant, and it is constant, or in the because it is constant, so in the examination this number will be given to you. So you have to use always 13,600 kilogram per meter cube for the mercury, if mercury used. If any other liquid is used, then you have to use the density. If let us suppose if this water is used, so for the water you have to use the density of the water, and this, because this is also constant, so this is also constant, so the value of the density of the water, it will be given in the question. No need to memorize this thing. Now the G, the last thing is, the last parameter is the G, and this G is the acceleration due to, this G is the acceleration due to gravity, and this acceleration due to gravity is also constant. It is also constant, and the value of the G, is, this is 9.8 and this is meter square. So this will be also given in the question, because it is constant all the time. For the earth it is constant. Now if you look at this formula, if you look at the formula for the pressure, this is HdG. So in this HdG, this D density, so this density is constant. It will be given to you, whatever the material or whatever the fluid is used in this barometer, it will be given. It is constant, it will never change for that medium, for that material, and the value of the G is also constant. It will never change. So here in this formula the two things are constant. The only thing is changing, that is the height of the mercury. And by using this formula you can find the pressure of the atmosphere, and this pressure, whenever you are taking the height in meter and you are taking the density in kilogram per meter cube and the acceleration due to gravity in meter per second square, then the value of the atmospheric pressure, it will come in the unit of the Pascal. Avogadro's number is denoted by Na, and this number states the Na equal to 6.02 multiplied by 10 to the power 23 molecules per mole. So what is the meaning of the Avogadro number? The Avogadro number is a constant number. This is this value for the gas, it never changes. So this is constant for the gas. Avogadro number is constant for the gas. So what is the meaning of this number? This number is Na. This Na is equal to 6.02 into 10 to the power 3 molecules per mole. Mole is the amount of the substance, we can say. So what is the meaning of this? If I say I have this one cylinder, and in this cylinder this is one cylinder, and this is the pump of the cylinder, and in this cylinder there is some gas inside this. So there is a gas here inside this. So these are the gas molecules like this. So this is the gas cylinder. And so how much gas? So the gas is measured in terms of the mole. Okay, so the amount of the gas, we say how much gas, the amount of the gas is in mole, we say in mole, how many moles. So if I say in this gas cylinder there is a 1 mole of gas, so the amount of the gas is 1 mole. So the Avogadro has given some number. He told if the gas amount is 1 mole, so in this 1 mole these are the molecules. So these are the molecules of the gas. So how many molecules are there? So according to the Avogadro number, in 1 mole there is 6.02 into 10 to the power 23 molecules are present of any type of gas. So it may be this gas may be oxygen gas, this gas may be CO2 gas, this gas may be nitrogen gas, any type of gas. If the amount of the gas is 1 mole, so in the 1 mole the number of the molecules are 6.02 into 10 to the power 23 molecules are present. Now if I say the number of the amount of the gas is 2 mole, so 2 mole means the molecules will be more. If the amount of the gas is like it is a double, so double means double, 2 times the number of molecules will be there. So in 2 mole of gas, the number of molecules are also double. So this is 2 into 0.23 into 10 to the power 23 molecules. So in 2 mole of gas, this number of molecules are present. So in 3 mole of gas, so the number of 3 moles of gas, so the number of molecules will be 3 times like this. 6.023 into 10 to the power 23 number of molecules will be present in the gas. So this is about the moles. Okay, and how many number of molecules are there in certain number of moles. But the Avogadro say, what the Avogadro has stated, he has stated in 1 mole, only in 1 mole. So in 1 mole 6.023 into 10 to the power 23 molecules are present in 1 mole of gas, This is the statement given by the Avogadro number. If the number of moles are double, 2, so it is 2 times like that. So here there is a relation between the number of moles and the total number of molecules in the gas. So this is the number of moles and the total number of molecules in the gas and the Avogadro number. So the relation between this small n and this n and the Na, it is the n equal to the small n equal to the capital N, and this is Na. So this is the relation between the number of moles, and this is the total number of molecules in the gas, and this is Na. So if I say there is a one gas cylinder, like this is one gas cylinder, and in the gas cylinder there is a gas. So inside there is a gas molecules are there. So these are the gas molecules, and the amount of the gas is, suppose say it is 5 mole. So 5 mole means the small n. So the small n is the 5 mole gas is there in the cylinder. So how many total number of molecules are there? Total number of molecules means in the formula this n, okay, this n, or sometimes we say it is total molecules are there, okay, you can say total number of molecules, or sometimes we say this is n, simply n. So you have to find what is the total number of molecules in this gas cylinder. So here what it is given here, it is given the number of moles are 5 and the Avogadro number is constant, so it is given. So the value of the Na is 6.023 into 10 to the power 23 molecules. So this is the molecules per mole, like this, and you have to find the value of the total number of molecules, this n. So by using this formula, we can find the value of the total number of molecules. So the formula will be like this. This is n equal to, this is after cross multiplying, so this is n equal to small n and this is Na, like this. So this formula we have to use to find the solution of this. Now how many number of molecules are there? So the number of molecules are, the number of moles are, this is 5 and this is 6.023 into 10 to the power 23, and this is 30. I am not taking the decimal, so this is approximately, so this is 30 multiplied by 10 to the power 23 molecules. So the value of the n is this. So the answer is total number of molecules in this cylinder is 30 into 10 to the power 23 molecules. Now we come to the second heading of this slide. This is STP. So this is S, T and P. So this is S, T and P. The meaning is the standard temperature and pressure. So what is the meaning when we use this word STP? So sometimes we say the gas is at STP. So what is the meaning of this when we are using this kind of language? The gas is at STP. The meaning, what is the meaning of that? So actually when we say the gas is at STP, so it means there are some default values of some parameter. Now if I say if I say a gas is at STP. So if I am saying like this, so what is the meaning of this? The meaning of this means in STP, this S means for standard, and this is temperature, and this is pressure. So when we say the gas is at STP, so the temperature of the gas you have to take 0 degree centigrade or 273 Kelvin, and the pressure of the gas you have to take 1 atmosphere. The 1 atmosphere is equal to 1.013 multiplied by 10 to the power 5 Pascal. So these values you have to choose, these values of the temperature and the pressure you have to choose for the gas. So if I say this is one cylinder, this is the cylinder of the gas, and the gas is inside. So this is the gas inside. So the STP, the meaning of the STP means the standard pressure, the standard temperature and the pressure. Ideal gas law formula. So ideal gas formula is PV equal to nRT. So this is a formula. PV equal to nRT is the ideal gas law formula. In this formula, this P stands for the pressure of the gas, and this is the pressure of the gas, and the pressure of the gas always you have to take in Pascal, not in any other unit of the pressure, not in bar, not in atmosphere, not in kilopascal, like that, Pascal only. And this, in the formula, this V stands for the volume of the gas, and the volume of the gas you have to take only in meter cube, not in liter, not in centimeter cube, not in millimeter cube. The only unit you have to use here, meter cube. This is the standard unit for the volume. Now this N stands for the number of moles of the gas. It has no unit, it is number only, like 5 mole, 10 mole or 20 mole of gas, like that. So it has no unit. And this T stands for the temperature of the gas, and the temperature of the gas you have to take in Kelvin only, not in degree centigrade. If it is in degree centigrade temperature, then you have to convert that temperature to Kelvin, and then you can use in this formula. And in this formula, this R is the ideal gas constant. This is constant for all the gases, and the value of this R, this gas constant, is 8.314 joule per Kelvin per mole for the ideal gas constant. Characteristics gas equation or general gas equation. So how we can define this characteristic gas equation or the general gas equation? We can define, provided there is no change in the mass of the gas, we can combine Boyle's law, Charles' law and the pressure law to give the general equation of the gas. So in this box it is saying when there is no change in the mass of the gas, it means if there is no leakage in the gas cylinder, no gas is going outside, no leakage, mass should be constant. So what we can do, if we combine the Boyle's law, there is a one law that is known as a Boyle's law, and another law is there that is known as a Charles law, and one more law is there, this is a pressure law. If we combine all these three laws together, then we get this kind of equation, and this is known as the gas equation or the general gas equation. So according to this equation, this PV divided by T is equal to constant, and this, if the meaning is for any gas, if I take the pressure of the gas and if I multiply this pressure to the volume of the gas and then divide the temperature of the gas, then whatever the value will come for that gas, it will never change. And also we have studied in the last slide the ideal gas law equation, that is PV equal to nRT. So you can see this equation, the ideal gas law equation, this is what this equation. This equation is PV equal to nRT. So if I take this T from here, okay, from here, if I change the side of this T, then this T will come here, this side. So this is PV over T, and this is equal to what? This is equal to nR. So this N means the amount of the gas. Okay, amount of the gas means there is no leakage, no gas is going outside, and this is also constant. So in this gas equation, this N means the amount of the gas. If the amount of the gas is not changing, meaning the gas is not going outside from the cylinder, or there is no leakage in the cylinder, so it means here it is constant, and this R is also gas constant. So these two parameters are constant, so it means this is equal to the gas constant. Now by using this information, we developed one formula for the gas equation, and this formula is what we are taking here. We are taking two stages of the gas, the initial stage and the final stage. So now by using this formula becomes the initial pressure Pi multiplied by Vi and divided by Ti is equal to the Pf multiplied by Vf and divided by Tf. So this PV over T. So PV, P multiplied by pressure multiplied by volume divided by temperature. So it means these values or these data. So this data is the initial data of the gas. This is the initial values. All these are the initial values. This I stand for initial. So this is initial values. Now here this is equal to, this is Pf, the final pressure, multiplied by Vf or the final volume divided by Tf or the final temperature. So this is equal to the final values. So this is for the final values. So what they are saying, if you take the initial data, initial values. So these are the initial values in the form of one formula, initial values, and this is same as the final values. They are same as the final values, like this. So here we are taking what we say this is PV over T. This is always constant, and we say this is PV and over T, this is always constant. So here we are taking the initial value of the pressure, and this is the initial value of the volume, and this is initial value of the temperature, and here the values are final values. So this is equal to, this is the final value of the pressure multiplied by final volume of the pressure, multiplied by final volume, and this is multiplied by final temperature of the gas. So this is the final pressure of the gas, final volume of the gas, final temperature of the gas. So this data is equal to this data always. So here this Ti stands for the initial temperature, and the initial temperature you have to take in the unit of Kelvin, and this pressure you have to take in Pascal. This temperature also you have to take in Kelvin. This pressure you have to take in Pascal. So this is the final pressure, and this is initial volume. So this initial volume you have to take in meter cube, standard unit, and this is final volume. So you have to take in meter cube. So these are the units you have to take while using this formula. There are three gas laws. The one is a Boyle's law, and the second is a Charles law, and the third one is the Gay-Lussac law or the pressure law. So this law is the first gas law, and the name is a Boyle's law. The first gas law is a Boyle's law, and in this box the statement of the Boyle's law is written. If in the examination question comes, give the statement of the Boyle's law, so you have to write the same language what it is given here in the box, same language like this. Don't write the formula. When the question says write the statement of the Boyle's law. Now what is the statement of the Boyle's law? The statement of the Boyle's law is the pressure of a given mass of a gas is inversely proportional to its volume when temperature remains constant. When the temperature remains constant. So in mathematical form, this is the pressure of the gas is inversely proportional to the volume. So in mathematics, what it is given here, this statement says the pressure of the gas is inversely proportional to the volume. So that's exactly same it is written here in the mathematical form. The pressure is inversely proportional to the volume. So this is proportional sign and this is 1 over V. But this statement will work on one condition. So this is the condition. This is the condition with this rule or with the Boyle's law or with this formula. If this condition is not satisfied, so this rule will not work. So what is this condition? This condition is the pressure of the gas is inversely proportional to the volume at the constant temperature. When the temperature of the gas is constant, otherwise this rule will not work. Now what is the meaning of this one? The meaning of this statement is, if the volume of the gas is increasing, if the volume of the gas is increasing, so it means if the volume of the gas is increasing, the pressure of the gas will decrease. This is the meaning of this statement or this formula. But this increasing volume and decreasing pressure, it will happen when this condition is met, when the temperature of the gas is not changing. But if the temperature of the gas is changing, then this rule will not work. This is very clear. So this is the condition for the Boyle's law. The temperature should be constant. And now what we can do here in the box down, okay, so here in this box down, what it is given here. So if I take this rule, the Boyle's law, so this pressure is inversely proportional to the volume. So if I multiply here this volume here, so it comes like this PV, and this is proportional to 1. This one is like a unit, or you say some kind of constant. So we can make one more rule. So this is PV is equal to K, like this, and here this K is any constant. This K is some constant, and this K is some constant, and it will not change for one gas. So the meaning is, if you take the pressure of the gas and if you take the volume of the gas and multiply together, what the answer will come, what the number will come, that is always same, that will never change. But this condition, but this formula is also true, this formula is also true when the temperature of the gas remains constant. If the temperature of the gas is not constant, so this rule will not work. So here it is the product of the product of the volume, the product of the volume and the pressure of a given mass of a dry gas is constant. So this product means the product means the multiply. So if you multiply the volume and the pressure, it is constant. So this is constant, but at the constant temperature. So this constant temperature is very important. And this is the condition for the Boyle's law. This is the condition of the Boyle's law. The temperature during this process, the temperature of the gas should not change, should not vary. Now what it is coming from here, this is inversely proportional. If I say this is increasing, so this is decreasing, pressure is decreasing, volume is increasing. So this we can see from the graph, and this is the PV graph. So we say this is the PV graph, the pressure volume graph. So this is the PV graph. So in the PV graph, I would like to tell you one thing. This kind of graph we can make like this. Okay, I can take the pressure here and the volume here, or I can take the volume here and the pressure here. So both the graphs are correct. There is no harm to take any parameter on any axis. Now on the x-axis, on x-axis, the pressure is taken in the unit of atmosphere, and on the y-axis this volume is taken in the unit of liter. So by using this graph we will come to know how the two parameters are changing. Now if you see this line, this pressure line, so on this pressure line some number is given. This is 1, 2 and 3. So if I compare 1, 2 and 3, so this 3 atmosphere, or this 3 number, okay, so this 3 number is the big number here. Okay, if I compare 1, 2, 3. So now the meaning is at this 3 means this is 3 atmosphere pressure of the gas. So what is the value of the volume at 3 atmosphere pressure of the gas? So how to find the volume? So you go to, and this is the graph, and you go up, and where this line is cutting to the graph you stop, then you move to the volume line, okay, like this, and it is going to 4. So it means when the pressure value is 3 atmosphere, the volume is coming 4. Now this is big value we have taken and some value coming here. Now what you do, if I take this is small value, okay, because this is 1, 2, 3, so 1 is a smaller compared to 2 and 3, so this value is a small value. So this is 1 atmosphere pressure. So at 1 atmosphere pressure, what is the value of the volume of the gas? So how to find? Okay, from this point, from this value, okay, you go up, and where your line will cut the graph you stop, then you move to the volume line, and this will come, and this is the volume is coming 12 liter, like that. So now this number is coming, okay, this 4 value, this 4 number coming here, and this number coming here. So this 12 is the big number on this line, we know, because it is 2, 4, 6, 8, 10, 12. So 12 is a big number, and this is the 4, so this 4 is a small number, like this. Okay, now if you see this 3 value, okay, so this is 3 atmosphere and this is big. So at the big pressure the value of the volume is coming small, and when the pressure is small, like small value, then the volume value is coming big. See this one. So they are opposite. When the pressure is small, then volume is coming big. So they are opposite. So the meaning is the volume, the pressure is inversely proportional to the volume, like this. And the shape of the graph is always like this. It will never change. The shape of the graph is always like this, always like this. So the shape of the graph, so this is the this is the volume here, and this is the pressure here, and this is the shape of the graph, which is coming downside, like this. Always the shape will be like this, between the pressure and the volume. This is a standard shape of the graph. It will never change. So if I say what is the shape between the pressure of the gas and the volume of the gas, so the shape is always like this. But this graph is true. This graph is true when the temperature is constant. Otherwise, this graph will not come like this. So this graph is at this condition. The temperature of the gas should be constant. It should not change. This is another form of the Boyle's law. Pi Vi equal to Pf Vf, or also we can represent this P1 V1 equal to P2 V2. So they are same, only here we are using the initial, this is initial pressure, this is initial volume, equal to this is final pressure, final volume, and here the initial and the final we are representing by the 1 and the 2. So at the place of this initial we are using 1, and here this is initial, we are using this 1, and for the final we are using this 2, and here for the final we are using this 2. So here let's understand how we take the initial and the final values. Let us suppose in this house there is a one AC, and the AC is off. So the temperature of the room is 40 degrees centigrade. So this is one temperature of the room, and when the AC is off. So when this AC is on, the temperature of the room will be decreased. Let's say it is 25 degrees centigrade. So here two temperatures are there, when the AC is off and when the ACs are on. So we say this is stage 1, the first stage, okay, the stage 1, or we say this is the first stage, and this is the second stage. This is the second stage, or we say it is stage 2. So we say this is stage 2. So I can write like this: the temperature T1 is, this is 40 degrees centigrade, and the temperature T2 is 25 degrees centigrade. So these are the two different temperatures at the different stages. So we can write the stage 1 temperature as a initial temperature, because initial means which is coming first, and which is coming first, so it means those parameters are the initial parameters, which the parameter is coming first, and the parameter which is coming after that or second, we say these are the final parameter, maybe final temperature, final volume, or the final pressure, anything. So the same information because this came first and this is second, so I can write like this: this is Ti, the initial temperature is 40 degrees centigrade, and the final temperature is equal to 25 degrees centigrade. So I can write in the form of the T1 or the T2 or the Ti or the Tf. They have the same meaning. So that's why the formula in this form and the formula in this form, they are similar. So you should know both the ways how the formula and the parameters are used in the formulas, because in the examination the parameters may come in the form of the I or the F, or it may come in the form of the 1 and the 2. So you should know aware about both type of parameters. And in what this formula is saying, what the Boyle's law says. Boyle's law says if you multiply the pressure and the volume of the gas, this is always constant. This multiplication will never change. And also this rule is true when the temperature of the gas is constant. So this always you have to remember. This would be now in this formula, this Pi stands for the initial pressure. This is the this is the initial pressure. So initial pressure we can write by Pi, or also we can write this by P1, and this is the initial volume, so we can write by V1 or the Vi, and this is final pressure, so this we can write by P2, and this is the final volume, so we can write by V2. So this way also we can write, and the standard units you have to use. Now the Boyle's law says if you multiply the pressure and the volume, so this is always constant. This is always constant, and this is also coming from this formula, from this rule, but with the condition when the temperature is constant. So we will see this thing, the pressure and the volume is constant, from the PV graph, which is given on the right hand side. So this graph is the PV graph. So this PV graph illustrates this is giving the information about the PV constant. So here this is okay, so this is the gas here. Okay, you can see the black points. So this is the gas, and this is the gas inside the gas cylinder, and here this is one weight. Okay, this is one weight here. So and you can see the volume. Okay, so this is the volume of the gas, and the volume you can see how much it is now, and this is how many weights are here. So the weights, the one weight, if I am putting the one weight, so it is giving some pressure value and the volume value. So this information is coming here. So if I say this is A point, so this A point, so at this A point, what is the value of the pressure? So if I drop down like this, so it will come here. So this is the value of the pressure at the point A. And what is the value of the volume? So I will go to the volume. This is the volume and this is the pressure. So here the volume is coming 4 liter. So this is here I have written the pressure is coming 1 atmosphere and the volume is coming 4 liter, and if we multiply this, so this value will come, PV value will come 4. Now come here. So after that, in this picture here there are 2 weights. So here there are 2 weights. If you are putting the 2 weights on this, the volume will go down. So you see the volume here, and you see the volume here. So here the volume is less. So it means the pressure should be more according to the Boyle's law. So we will check. So this, okay, if I say this is represented by the point B. So at this point B, the value of the volume, the value of the pressure is coming 2 atmosphere. So this is 2 atmosphere, and the value of the volume is coming for 2 liter. So this is 2 liter and this is 2 atmosphere. So this is 2 atmosphere here and this is 2 liter here, and if I multiply, so this will come 4. So this PV is coming 4 here. Now here in this picture, here there are 4 weights. Okay, more weight means more pressure, and more pressure means, so more weight means more pressure. This is more weight. So more weight means more pressure. So this P is more. So the Boyle's law says if the pressure is more, then the volume should be less. So here if you see the volume is very less here. See this volume. Okay, so we can find the value of the pressure and the volume. So let's say this point representing this picture. So let's say this is the C, and at the C point the value of the pressure is coming 4 atmosphere, and the value of the volume is coming 1 liter. So this is coming 1 liter here. Now I have written here the pressure the pressure is 4 atmosphere and the volume is 1 liter, and if I multiply, so this is coming 4. And what we are doing here in A, B and C, this weight we are increasing, so the pressure is increasing. So you can say if the pressure is increasing, so the volume here, it is decreasing. This is very clear from this graph. Now if you see for the point A, so at the point A from the graph, if I collect the data, let's collect the data from the point A. So this is from the graph. So this is from the PV graph. This is from the PV graph, and this is for the point A. For the point A, the value of the PV from here. So the value of the PV is coming 4. So this is coming 1 multiplied by 4. So this is coming 4. Now if I go to the B point, so the B point, the value of the PV is coming here, again it is coming 4. So this is again coming 4 here. Here this is 2 and this is multiplied by 2 and this is coming 4. And if I go to the C point, so for the C point, for this point, this is coming 4. So here this PV is equal to, it is coming 4. And here the value of the P is 1, and this is 4, and this is equal to 4. So if you see this, at the different points on the graph, like here, so this is V and this is P. So this is A point and this is B point and this is C point. So at the different points in the graph, the value of the PV is constant, it is not changing. So in this case it is coming 4. So here the value of the PV is coming 4. So this is constant everywhere on the graph, and this is constant for one gas. If I change the value of the gas for one gas, if I change the value of the gas, maybe this value not 4, maybe this value 10, but this 10 means it is 10 same for all the graph, everywhere on the graph. Whatever the number is coming here, so it is same for everywhere. So what changing here, if you see the pressure value here and the volume value here, and and the pressure value here and the volume value here, it is not same. Pressure, see this pressure here, and see this pressure here, and see this pressure here. So they are not same in A, B and C. The pressure is not same at the 3 points on the graph. And if you see the volume here, the volume is 4 and the volume is 2 here and the volume is 4 here. So also the volume is not same at the point A, at the point B and at the point C, but the multiplication together, the multiplication is not changing. Charles' law, the statement of the Charles' law is the volume V of a fixed mass of a gas at constant pressure is proportional to the temperature T. So this is the statement of the Charles' law, and from the examination point of view, already I told you while discussing about the Boyle's law, in the examination, if the question says write the statement of the Charles' law, so you have to write this language you have to write, not the mathematical formula. This is the mathematical interpretation of the Charles' law, this and this, but don't write the statement in this form and in this form. So statement always be in the verbal form, in the words you have to write, the correct form you have to write from the examination point of view. So what this statement is saying, this statement says the volume V of a fixed mass of a gas at constant pressure is proportional to the temperature T. So the temperature, according to the statement, the temperature and the volume, they are proportional. So this is the mathematical form of the Charles' law. So this says the volume is directly proportional to the temperature. So if the meaning is if the temperature is more, the volume is more, but there is a condition with this rule, with this law. At the constant pressure, the pressure of the gas must be same, must be constant, not change. So if the temperature is double, the volume will be double. If the temperature is half, then the volume will be half, like this way. So in the same order it will change. If the temperature is going, suppose 1/4, so the volume will be 1/4. If the temperature is going 5 times, so the volume will go 5 times. But this will happen when this condition met. So this is the condition for the Charles' law. What is the condition? The condition is, this is the condition, the constant pressure, this one. So here now from this rule it is given like this. Now this the volume is directly proportional to the temperature, so I can write this one like this. So this is V over T, this T will come down and this is proportional to 1. So this one number is like here, it is a unity, or sometimes we say this is some kind of constant. So from here we are getting the ratio of the volume and the temperature. The ratio of the volume and the temperature is always constant at the constant pressure. So this rule also says if you take the volume value and if you take the temperature value, so whatever the number will come, this will never change for the gas, but this should true when the pressure of the gas is constant. So this ratio is always constant when the pressure of the gas is constant. So this we can check from the graph, and the graph is given on the right hand side of this slide, and you can see here in the picture, this is one cylinder and this is also one cylinder, and this is the pump here. This is the pump of the cylinder, and here these are the gas molecules, and say some temperature is here, and this is also the gas cylinder. This is the pump of the cylinder, and this is the gas molecules here. So here no heating. Okay, so we are not heating the gas here, so no heating means some temperature is there. Okay, let us some small temperature, and this is the volume of the gas. You can see the volume of the gas, and the pressure of the gas, is 1 atmosphere. So you say this is case A. This is case A, this one. So in the case A, the pressure value is 1 atmosphere, and some volume is there, and say some small temperature because no heating. And here this is the case B, and in the case B, this is the heat is going into the gas. And now when the heat is going into the gas, so this pump is going upside, the pump is coming here. Now this is the volume of the gas. You can see this volume, and you can see this volume. So here this volume is bigger, this volume is more, because this temperature is more, because here the gas is heated, so that's why it is more. But this pressure here, it is 1 atmosphere, and here also in this case also the pressure is kept constant. So in case A and in case B, both the side the pressure should not change, otherwise this rule will not work. And there is a graph, Charles graph, or we say it is a VT graph. So the standard graph between the volume and the temperature for the Charles, so this is known as the VT graph. So this is the volume temperature graph, or this is also we say the Charles graph. The Charles graph is between the volume and the temperature. So this is the temperature here, and this is the volume here, or anything we can take on any axis. I can take here, I can take here as a I can take here as a volume, and here I can take as a temperature. So there is no harm in both the cases. The shape of the graph is like this. If I take this T and this V, this is like this, and if I take V here and T here, the shape of the graph is always like this. So the meaning is, if the temperature is more, the volume is more, like this. It is like this. So this is the VT graph, and the shape of the graph is like this. but this shape is true, this graph is true at the pressure constant. The pressure of the gas should be constant. So this is about the graph, and I have one graph down, and in this graph we are going to study this rule, this one. We are going to study, okay, how this rule is coming, this one. Okay, how this is coming constant. So how this is coming constant. So we will see this from the graph, and from the graph it is coming like this. So from here the graph is between the temperature. So this is the temperature here. And one more thing, this volume should be the unit of the volume, the unit of the whenever we calculate. So this unit should be meter cube and this unit should be Kelvin, like this. So now here we are so this is the Charles graph, and this is on the x-axis is T and the y-axis is the volume, which is given in the unit of milliliter. This is the unit milliliter. So for the comparison we are not going to change, because here as an example we are comparing only, and this temperature is given in degree centigrade, but for the comparison this should be Kelvin, not degree centigrade, but this graph is given in degree centigrade. From the examination point of view, the graph may be given in degree centigrade or the graph may be given in Kelvin. So if it is given in Kelvin, it's okay, no issue for that one, but if it is given in degree centigrade, you have to change. So from the examination point of view, any parameter may come anywhere. So what I have to do here, I have to prove this rule. Okay, so the ratio of the volume and the temperature is constant for one gas, it will not change. So we are taking this formula and from the graph, so this is we are going to the VT graph, and we will take some points and then see, okay, how the ratio is coming. So I am taking this, suppose if I say this is point A and this is point B and this is point C. So here I am writing the data at, so this is, I am taking, this is for the point A. So for the point A, what is the value of the temperature? So the temperature is here on the x-axis, so you come down and see, okay, where this line is cutting on the temperature axis. So this is the line is cutting at minus 75. So minus 75, so this is minus 50, so this is minus 75. So this temperature we have written here, the temperature value is coming minus 75. And what is the value of the volume at this temperature? So at this temperature the volume is coming, this is 400 milliliters. So this is also written here. So at the point A, the volume, this is 4 milliliter, I have written here, and the temperature value is coming, this is minus 75 degrees centigrade. So this centigrade I cannot take, so what I have to do, this is minus 75 and this is plus 273, so make it Kelvin. So let me calculate this one. So this is minus 75 and plus 273, so it will be 198. So this will come 198 Kelvin. So these are the parameters which are given at the A point. Now what I will do, I will take the ratio of this. So this is V over T and this is equal to, let's take 400 milliliter, so no issue here for the comparison. So this is 400 and the temperature is coming 198 and the value is coming, so this is 400 divided by 198, so it is coming to, this is coming to 0.02. So this is the value of the ratio of V over T at the point A. Now we got this one. Now after that we have to choose one more point, and then we will check the ratio of the volume and the temperature. So this graph is coming, this graph is coming when the pressure is constant. This graph is coming when the P is constant. This is very clear. P constant always. So let's take the point B. So for the point B, okay, so here I am taking the point B. So for the point B, now if I come down, so this is the value of the temperature. The value of the temperature is coming, this is 0 degrees centigrade, and in Kelvin this is 273 Kelvin, and the value of the volume is coming, so at this point, and this is coming, actually the scale is not very exactly given, but it is nearby 551, something like that. So here for this B point, this is the value of the temperature, 0 degree centigrade, and this is the value of the volume, 551 milliliter. So from the graph, I am taking the value of the volume, so this is 551, this is milliliter, and the ratio, this is V over T, and the V is 551 divided by 273, and let us calculate the ratio. So this is 551 divided by 273 and divided by, it is coming 2.01. and now this is the data, this is the ratio of the volume and the temperature at the point B. Now go to the point C. So for the point C, the temperature is coming, this temperature is coming, this is 50 here, this point is 50, so this is coming 75, and this 75 is written here, this 75. So this is, okay, I am taking the point C here, this is point C. So this is the temperature value in degree centigrade, it is coming here, okay, from here to here it is coming, so this is coming 75 degree centigrade, and the value of the volume at this temperature, it is coming 700 or close to 700, but exact value here it is taken, so this is 703 milliliter. So I will write the data for this one. The temperature is coming, this is 75 degrees centigrade, but this we cannot use, so this is 75 and plus this is 273, so this is equal to, after the calculation, so this is 75 plus 273 and it comes 348. So this value is coming 348 Kelvin, and here the volume value is coming, this is 703, this is milliliter. Now find the ratio of the V over T. So this V over T is, this is 703 divided by 348. So let's calculate the value of this. So this is 703 divided by 348, and it is coming 2.02. So this is coming 2.02, and this is the ratio of the volume and the temperature at the different point. Now let's do the analysis at the point A, point B and point C on the graph. So if we analyze this point A, point B and point C, so the ratio of the volume and the temperature, so in the point A, this value is coming 2. So this value is coming 2.02, and for the point B the value is coming 2.01, and for the point C the value is coming, this is 2.02. so if you remove the decimal, because decimal value is very less, so the value is coming 2. So for the point A this is 2, and for the point B this is 2, and for the point C this is also 2. So it means at the points A, B, C on the graph, the ratio, this value, the V over T is not changing. So this is at different points, this value is coming constant all the time. So this is the property of the Charles law. The Charles law says if you take any point on the graph, any 1 point, 2 point, 3 point, 4 point, any number of points if you take on the Charles graph, so the ratio of the volume and the temperature at those points is constant, it will never change. And the standard shape of the graph is always like this one. So the Charles law, for the Charles law, there is a VT graph. This I already told you. The shape of the graph is always like this. So this is the temperature axis and this is the volume axis, and the shape is always going upside. So the shape is, this is the standard shape of the Charles law, VT graph we say, and this is a graph between the T and the V. But whenever you are drawing this graph, so you have to write the pressure is constant like this, like the graph which is given here. Okay, so in this graph, this is a graph between the volume and the temperature, and you can see the shape of the graph, this is always like this, never it will be away from this graph. So the shape is always like this. This is the shape of the Charles graph, the Charles law, always straight line, and never this line will be like this, or never it will be like this. It is always the straight line, how it is shown in the graph, like this. This is the correct way to show the Charles law. Equation of Charles law, or another form of the Charles law. So this is the Vi over Ti equal to Vf over Tf, or we can write in the form of 1 and 2. So this is V1 over T1 is equal to V2 over T2. So here this is the initial volume divided by initial temperature, and this is final volume divided by final temperature. And here already I have discussed that you can use initial as a 1 and final as a 2. So this is V1 over this is T1 and equal to this is V2 and this is T2. But this will happen, this is true when the pressure of the gas is constant. So this is at the constant pressure, and this is initial temperature, or you can this is initial temperature, or you can do like this. So this is T1 and this is V1 and this is T2 and this is V2, like this way. And on the right hand side of the slide there is a VT graph, or the Charles graph. So this is the graph between the volume and the temperature, and the graph is a straight line graph. This is a straight line. So it means what information is coming from this graph. So if the temperature is increasing like this, so the volume is also increasing, so both are proportional. So what we can say from the graph, that the volume and the temperature, both are proportional. So this information is coming from this graph.